speaker is László Zhilinszky. He's coming from University of North Carolina, Feb. He's gonna speak on his topic is on some topological games. We are very happy to have him here these days. So, thank you.
First, let me thank as well as Peter, the organizer, for inviting me to have a chance to talk a little bit about some old stuff, and if I don't have time, maybe I'll touch on how my research relates to these ideas. I'll try to start with a simple material, and with the gentlemen. We are in 1935 Poland. Stanislav Mazur is now a famous name in math, and he had a companion. They for some reason are always together in the literature. Mazur and Stefan Banach, and especially the second guy, Banach, is a fixture in results. Starting, he single-handedly invented parts of functional analysis and stuff. But what they also did, they had this custom of drinking a little bit here or there. And they had this place. Somewhere in Poland, Warsaw, I guess. Their favorite place where they sat down and I think Poles drink beer, maybe wine, I don't know, whatever. It was alcoholic, I'm pretty sure, because Mark was famous for that. The guy was a genius. Both were geniuses. I mean, they were unbelievable characters. And I have a Polish colleague, so whatever I'm saying is coming from a perfect source. And allegedly, Banach was able to do these things only if he was not completely sober. So that was the place for doing the math. And they did not always pay. But the owner of the club knew that these guys are geniuses, so whatever they are coming up with, maybe historically will be useful. So they had this book where they wrote down their mathematical ideas and conversations, and the so-called Scottish book, which was put down. The Scottish book, they couldn't take it with them. It was in the hands of the owner, especially if they didn't pay for the bill. That was the thing, because Banach had a tendency to forget what he was doing under influence, so it was in that book, so that was his card. But anyway, one of the results they published and later on in this Scottish book was proposed by Mazur, who proposed the following thing. Let's take the open interval 0, 1 and pick a subset, and a collection of numbers between 0 and 1 and stack it inside set A, and then let two players, call them alpha and beta, play the following game. They both will choose open subintervals within that interval 0, 1. So we start with 0, 1. There is something here which I call A. I fix that as I'm going to change, and then here comes player number alpha, and he's supposed to pick an open interval inside 0, 1. That's what I call the U's will be alpha's choices, and the B's will be beta's choices. How it is supposed to be done? It is supposed to be done in such a manner that let's say that the first player alpha chooses U0, and then the second player beta chooses another. The rule says the second guy's choice has to be inside the first guy's choice. So we are nesting intervals and keep doing it. So now alpha chooses again inside the previous choice. It doesn't have to be in the middle, it can be shifted sideways, it can be of any side. All you have to do is to be an open interval inside the previous open interval. And you keep doing it until the natural numbers allow you to do that. So for every natural number, n, you will make a choice. The u's and the v's are intertwined, nested. Okay, so that's the game. But you're playing for something, so you also have to have a rule. The game ends with alpha's win if the intersection of all these open intervals. So you're collapsing, you're zooming in with your choices. If there is something in all your intervals, if you are zooming in into a specific value, at least one, and this specific value is one of the elements of your set, if alpha can force that kind of a choice, then alpha wins the game, that run of the game. If not, the other guy wins. Whenever you play games, especially in zoology, you are interested in knowing, it's not just about randomly picking things. I mean, that would be meaningless. The question really is, does alpha or beta have some kind of a choice, some kind of a magic knowledge? Is there some kind of a magic knowledge which will ensure a win, no matter what the opponent says, no matter what the opponent plays? This clearly can happen sometimes. What if, for example, A, this chosen set is empty? There's nothing in there. What if A is empty? I didn't specify what A should be, so it can be empty. Then, no matter what alpha does, beta is going to defeat it. Why? Because no matter what those intervals will be, the condition is that for alpha, the good condition for alpha is that the intersection of those things have to meet A. But there is nothing in A, so there is nothing to meet. So there is no way to produce a non-empty intersection. But that was a very weird sub-case. But think about another non-empty case. So what about if you take a single point for A? So what if you are like this? What if you start 0, 1, and you pick a point, and this one point is what is inside A? Then, okay, the first guy, alpha, wants to intersect, so it's in his interest to include that A, because if he chooses something here, he lost already. So his interest is the first guy's interest is to include that point, because he wants to intersect there. But it doesn't matter, because there is just too much room in that interval. So what if the second choice of alpha is this one? And it doesn't matter where that point is. Once the second guy chooses this one, the game is over. There is no way that the intersection of these intersecting and interlocking intervals will ever meet in that single point. And you can play the same game if you have any finite amount of points in A. You can play the same game if you pick a sequence inside that is 0, 1 open interval, which is not finite, it's beyond finite. We call it countable. And there is this one countable set inside 0, 1, which is very active. It is all over the place. If you take all the rational numbers, all the fractions inside 0, 1, if you took some more advanced real analysis or advanced calculus course, you probably learned that the rationals are everywhere. No matter what interval you take, you will be able to find the rational number. You say that the rationals are dense in 0, 1. But that's just a countable set. Also, it is possible to label the rationals by natural numbers, so that's what countable means. And you will be able to do it as well. Do what? To make sure that beta wins. Beta will have a so-called winning strategy. Strategy is that magic information that one of the players have or not. Strategy is a choice, a function. Actually, if you do the math, you can define it as a function, which tells the player how to choose the next open interval given the previous information, the opponent's information, so that you win that thing. And you win every single run of the game, regardless of the opponent. So, just a couple of examples, it should be clear that everything depends. The outcome of the game kind of depends, at least for beta, depends on what set you choose. You can now overchoose it. You can, for example, take A to be everything in 0, 1. And you can ask yourself, okay, so what about them? Because if you take everything, then these intersections, if they happen, they are automatically in A, because A is everything. But it happens to be the case that the intersections of open intervals are not always non-empty. Think about taking these open intervals. Take the 0, 1, 0, 1 half, 0, 1/3, and so on. Go with 0, 1 over n. These are all open intervals which are inside the 0, 1. So these are possible good choices. But these guys will never intersect in anything, because the only thing that is common to each one of these intervals is 0. But 0 is not a, it's an open interval. So the intersection of countably many open intervals is not necessarily non-empty. So it's a little bit more complicated. It turns out, and this is Maslow's result, is that what matters is the notion of the Noether dense set and what you can build from it. I said this Noether dense. I said the rationals are dense, meaning that any open interval will contain the rational. I said it's not dense if not every open set contains an element of that set. And it's Noether dense means that no matter what interval you take, you will be able to find another interval which misses the set. So a Noether dense set is pretty meager, pretty weak, pretty not present anywhere or everywhere. Now if you take those kind of guys and unite them, then you get a so-called first category set. And if a set is not first category, again, the first category still should be viewed as something meager. You know, it's spread out on the 0, 1 open interval, but it's not present everywhere in some sense. The second category set is just a set which is not first category. So that's the opposite. That's the now. Once you talk about categories, categories of sets, there is no third category, just first and second always. Then you are deeply in beautiful applications throughout all over math. Peter talked about smooth curves and smooth functions that have derivatives everywhere. That was one of the big results of the 19th century when they tried to make sure that they know what they're talking about as far as calculus and analysis is concerned. And one of the questions, for a long time actually, people thought that continuous differentiable, not that big a deal, not that big a difference. Differentiable should be viewed as a a function is differentiable, it has a derivative. To have a derivative means that you are able to post at every point you are able to post a tangent line. So if you have sharp terms, like Peter said, you cannot put a tangent line in there because there is no firm position. So the question was, okay, can we come up with this? Because sharp turn still means continuous. Discontinuous means hole or gap in the graph. Sharp turn, there is no hole or gap, so it's continuous, but there is no tangent line at that spike. So the question was, can we produce a function that is continuous but not differentiable? Yeah, at concrete points, not such a big deal. Like in a sharp turn case, that's a typical case on what you probably learned in calculus, that this is a function. The absolute value function is a function which has no derivative at 0, but it's continuous everywhere. But here is the big question, and the big answer, the big result, is that you can actually produce a function that is continuous everywhere, so no hole theoretically in the graph, but differentiable nowhere. You cannot put a tangent line anywhere in that curve. Now I will not be able to graph it for you because it's a very theoretical construction, but there's a formula, and the guy who came up with Bolzano, I think he didn't even publish it, he just did a story about it. The first guy who published it was Weierstrass, but now everybody knows that both kind of came up with the same thing, so it's called the Bolzano-Weierstrass result. And they have some other results like that. But what I'm trying to say, and that's why I'm talking about this thing, is that the idea, and there's a machinery, there's a procedure in math that people use using categories, first and second category sets, and especially second category sets. You can use that idea to produce such a function, not by giving a formula, because that's very, very non-trivial to actually produce a formula and then check out this formula does the job, but by an iteration process Basically, your job is just to create the foundation of your idea wisely enough, and then this idea of the category set in due process will eliminate all the bad stuff, and what's left in the intersection of your collections that you care about is exactly what you wanted to begin with. So it's not a ready-made thing, but it's an approximation of ideas kind of thing, and that is very useful. It's all over the place. Now, it turns out that Mazur was able to prove that if that set A is of first category, whatever that means, and all the examples I gave you, the single point, finite millipoints, sequences, all the rationals within 0, 1 are of first category, but there are some other non-that trivial cases which are also of first category. It turns out if you have such a set, indeed, beta will have a winning strategy in this game. Beta will always be able to win. There is this magic knowledge out there for beta, and alpha can know, and alpha will probably know the same thing, but if alpha is dealt a set of this kind, it's over from the get-go. So basically there is no reason to play for alpha. But the question was, okay, what about, is it true though, is that that's the only way for beta to win? Is it an equivalence? That's where Banach came into the picture, and allegedly he proved that and it's recorded. It was not published by him. This was just a game for them. They played these games in the pub. But he managed to prove that that is indeed the case. It goes both ways. Beta has a winning strategy if and only if that set is like that special kind of a set on the 0, 1 open interval. Naturally, you can ask yourself, or they did, and they answered this question as well. What about alpha though? How can alpha make sure? What should A look like, or what should the complement of A look like for alpha to have a winning chance, no matter what beta does? And there is a result, but I don't want to go into that part because it's irrelevant for me, because that's not what I'm trying to talk about here. There is nothing else to say. It's over. I mean, the result is there, and it was there in the 1930s already. The game is over. None of this was published, by the way. It was stacked away in the Scottish book. It was mentioned there. All the ideas were there, so if somebody was interested, and knew that the owner of the pub, they could probably read this thing. And it was, the terms were not that well defined like they are now. There was no lower 10 set problem back then. The notion of the strategy, until recently actually, it was all over the place. People defined these things differently. The first guy who managed who published it and then defined the modern way these ideas was Huxley in 50 something. When he actually showed, you see, it looks like the same answer, same result as the first two put together because it's an equivalence. But what he noticed that you do not have to play this thing on 0, 1. 0, 1 is natural because everybody understands, everybody can relate to 0, 1. But mathematicians go beyond 0, 1, way beyond 0, 1. There is such a thing as a metric space, if you want, which kind of mimics some good properties of what you learn from a distance on the number line. But even more generally, you can talk about so-called topological spaces. Topological spaces are spaces where the properties of your subjects and collections kind of mimic what you like about open intervals on the real line. So in topological spaces, you have so-called open sets. There are some conditions that tell you what a good open set should satisfy, and once you have those properties satisfied, then you declare your space a topological space. This is pretty much the same idea. If you took linear algebra or a little bit more advanced course, I'm talking about the students mostly here, then everybody started, all math started in the real line one way or the other, as far as the structures are concerned, and then you take two real lines and you create a Cartesian plane, and suddenly you can build vectors because they are of some importance. There are these arrows that have directions and sizes, and and they have some application. And then you can create arrows in three-dimensional space. And then you realize that there are some properties that you care about these arrows, which are pretty similar to some properties that you care about the real numbers. And then somebody else goes, well, there are these matrices, so-called matrices, which pretty much satisfy the same kind of properties. And then there are these polynomials that do the same thing. And there are other creatures. And instead of talking about matrices, polynomials, real numbers, vectors, you just say, well, let's all call them vectors. And whatever these 10 or 11 properties that you care about for vectors to satisfy will be posted and highlighted, and everybody who satisfies those things will be a member of a vector space. That's how the relationship between open intervals and what I will call the topological spaces. What László realized that the same thing, and basically there is no need to change a lot or basically anything, will go through in any such S. You don't have to have a 0-1 open interval. You just take this very, very general notion of the topological space, and you can play the whole thing, and you can actually have the same result. So again, there is nothing else to talk about. However, by this time, and everybody knew that the second category argument is really useful in math. Famous theorems use the idea, including involving category arguments. So the question was, can we build some understanding through these games, through some kind of a game? The game is played step by step. You don't have to just have this magic knowledge of knowing everything from the get-go, but the game may just step by step lead you to the right thing. That's the beauty of it. In not finite many steps, but reasonably, countably many steps. That's still manageable. And the answer is yes, because of the sources. The game that does a very good job in achieving these goals is the so-called Banach-Maslov game, which can be played on any topological space, whatever that means. Like this. Same idea. I'm not going to call the players alpha and beta for the sake of this call, but I'll call them player 1. For the sake of this talk, I will call them player 1 and 2, but they are like alpha and beta. And let's say that player 1 chooses an open set. This black circle represents, black disc represents that first choice. It's like that first interval that was chosen before. And then player number two chooses another open set inside the first one. So I'm trying to use the same idea as I go along. Notice that what I did not do here for this game, I did not specify a set that I want to meet at the very end. I don't care about it because I'm just going to specify the winning rule in a different way. But again, so you keep playing the game 1 and 2, you choose those sets, not in the middle, somewhere. But you have to make sure that it's always inside the previous choice. And you don't stop here because you keep doing it like in the previous game, counted many times. The question is, how do you know one or the other wins? Player 1, the first one will win if the intersection is empty, period. No meeting A or not meeting A. Just make sure that the intersection of your sets is empty. And if you can do that, 1 wins. Otherwise, the second guy wins. Otherwise, it's non-empty. So this is just a tool because you don't specify that A, there is either one choice or the other choice. This Oxford gentleman, and he is also very, very well known as name in topology. He has this beautiful book he wrote, and actually that helped me to get the feeling I have about topology right now, because it's really a nice tiny book and with a lot of dense material, beautifully written. Anyway, he and this other guy, Crom does not have too many papers after this thing, but this was something that he realized, that in this new game, the so-called Banach-Maslov game, player 1 has a winning strategy, BMX, I denote the Banach-Maslov game, if and only if X has a non-empty open first category subset. set. Okay, first category I define. First category should trigger this idea of something meager, something weak, weakly spread in one way or the other, in some sense. And I define, you can define what that means. It doesn't mean that the whole thing has to be like that. It just means that your space has to contain something weak, something meager. If that happens, you are done, as far as player one is concerned. And this is where the idea of the bare space comes into the picture, because the opposite of this condition where player one wins is exactly what bareness is. A bare space is a space which does not let you have an open neighborhood with this weak little property of one first category. Namely, an empty open set must be a second category. If you can show about a space that it's a bare space, that means that it's effective non-empty. And things happen for you more readily than otherwise. So this is a very good property in math and used very frequently. If I rewrite, therefore, absolute result, I can, from the bare point of view, it basically says that the space is bare space if and only if player has no way of winning. What about player one? Player one is harder to, and player two is harder to decipher. Player two, we have some special cases when we know something about it. So this is still the big question of characterizing when player two has a winning strategy, is completely out of our bounds. It has a winning strategy, and this is a little bit more technical for students, if and only X contains a so-called dense. Dense means everywhere, every open set has an element, completely metrizable subspace. Completely metrizable, again, an important completeness property that shows up in math. This is much stronger than bareness. For player two to win, if player two wins, clearly player one doesn't win. So if this player two wins, then this happens, then player one does not win, and therefore anything like this, if player wins, the space must be a bare space already. And I cannot tell you a lot more because my time is up, but let me just go through some interesting results which are out there. There are spaces, and one of the spaces is the so-called Bernstein set. This is, and for students, this is not that easy to comprehend what this set does and how it looks like and how to construct it, but there is a thing like that. And that's a set which has a weird property. If you live in that set, if you live in the topological space, neither of the two players have a certainty to win. The game is undetermined. You cannot predict, there is no magic bullet for either of the players to win. If one of them wins, the other one cannot win. But undetermined, that's really tricky. And that happens with this game. There is another thing that I want to mention, I'll stop right here. I talked about the notion of the strategy for a player. Strategy is when a player knows everything that the opponent did before, from the first step all the way to the previous one. What people call sometimes a tactic for a player, or in the literature they also use a stationary strategy, is when you don't know, either you don't care or you don't know for some reason, everything that has been played before by the opponent, only the very last step. And then the question is, okay, does it matter if you know just the very last step, or you really have to know everything before, the perfect information of the game, to have a chance to win? And it doesn't matter for player one. If player one wants to have a tactic or a strategy, it's okay, because either way it's the same answer. Player two is different again. There is a space, and that was the guy who came up with two examples. The second one is really, really complicated. But actually you can have a winning strategy and no tactic. So actually it matters if you have that power or not in the general picture, and not like player one. think I'm pretty much done. So let me stop here. I wanted to talk about another game, but I lost my time in those pictures, so it's meaningless to even talk about. This is just the tip of the iceberg. I mean, people are talking about this game, and there are all kinds of other games for all kinds of purposes. This is a very useful idea in math. Thank you.
If you have any questions for Professor Zhilinszky? What kind of drink they used to
I don't know that. I just know that
if
it's
we don't know
alcoholic. That's all I know.
Let's have him in